In this video, we're going to do a full example of a convolution problem using the convolution integral. So we're going to convolve x of t and h of t, as you can see here, and these are signals that we've convolved in a previous example where we exploited the derivative shortcut. In this case, we're not going to exploit the shortcut. We're just going to do the problem out the long way. And I'm going to start by reminding you that the formula that we're attempting to apply here is the convolution integral, which is defined as the integral from minus infinity to infinity of x of tau, h of t minus tau, d tau. We've derived that in a previous video, where tau is a dummy variable. And the first thing to notice is that one of these functions is going to get flipped across the y-axis because we have a minus tau. That's going to be my new independent variable as tau, and if I have a minus tau, that means I flip it. And just based on a little bit of experience, I know that flipping x of t will be easier than flipping h of t for this particular problem, because x of t is a constant, so if you flip it, it's still going to be a constant. Whereas flipping h of t, you're going to have to muck with the formula a little bit more. But either way is fine. And I'm actually allowed to swap these because if you remember, the convolution of x of t and h of t equals the convolution of h of t and x of t. So in other words, the order doesn't matter. So in order to make this a little easier for myself, I'm going to pretend that this is h of t and this is x of t. But in the end, it doesn't matter. I could do it either way, and as long as I apply the formula correctly, I'm going to get the right answer. So my approach is essentially to just go plug and chug for each of the terms of the integral and then see where that gets us. So the first thing I need is x of tau. Well, to get x of tau, I'm going to start by looking at x of t, and it turns out they're basically the same thing. In fact, all I'm going to do is I'm going to rename my x-axis from t, I'm going to rename it to the dummy variable tau, and so this will now become x of tau. And if I draw my plot, it'll look like this. Alright, and that's the tau axis. That's still 1, that's still 1, and the equation of the line is now, instead of 1 minus t, it's now 1 minus tau, because I've changed the value, I've changed the name of the independent variable. Okay, so that takes care of the x of t term. So the next thing I need is the h of t minus tau term. So that one's a little trickier. In order to establish that, I'm going to work over here in the margin for a moment. I know what h of t is. Let's see if we can go step by step to work out what h of t minus tau is. So if h of t is the plot we see over on the left, then the first thing we can do is specify what h of tau equals. And in exactly the same way that x of t and x of tau are the same thing, well, we can say that h of t and h of tau are also the same thing. So this will be h of tau, and this will, oops, I wrote t. I said tau, but I meant t. No, the other way around. I said t, but I meant tau. There we go. That'll be h of tau. So the next thing I'll want to do is I want to get h of minus tau. And as we've learned in just about every math class we've taken, if you negate the independent function, then the effect is to flip your plot across the y-axis. So it'll look like this for h of t. So that'll be 0, and that'll be negative 1, and that'll still be 1. And then the last thing we need to do is we need to do h of t minus tau. So h of t minus tau works like this. If you have an independent variable of tau, then with respect to tau, t is a constant. And we know that if you add a constant to your inside your parentheses, then that has the effect of shifting your plot. Okay? So in our case, it would look like this. I'm going to be shifting it by t units, so that 0 will become t plus 0, and this minus 1 will become t minus 1. So all I'm doing is adding t to both terms. Okay? So that's a lot of steps, and in the future when you do these problems, you can actually just go straight to the answer. In effect, all I've done is I've taken my h, I've flipped it across the y-axis, and then I've added t to both of the to all the values. So for example, the way I've drawn it down here, you can see that I'm using a negative value of t in order to shift it to the left, but I can also use a positive value of t and shift it to the right. Okay, t can take on many different values, and in all cases this will still be t and this will still be t minus 1. It just depends on what the value of t is. So having worked all that out in the margin, let's go ahead and draw h of t minus tau. So here we have h of t minus tau, and if I draw that out, it's going to look like this, and I'm going to pick a negative value of t for the time being. In a moment we'll challenge that assumption, but for now let's say this is t, this is t minus 1, this y value is still 1, and for this red plot that I'm drawing, we're going to assume that t is negative. Okay, if t is negative, then my plot will be shifted to the left the way I've drawn it. And now we have h of t minus tau. Good. Now according to the integral, according to the formula, the next thing I need to do is I need to multiply together x of tau and h of t minus tau, and then I need to integrate whatever's left. So in this case, if I multiply x of tau and h of t minus tau, it's actually going to be 0 for all values of tau. And the way I know that is that any time you multiply a function by 0, you get 0. So in this case, over here, I've got h times 0, so that'll give me 0. And over here, I've got x times 0, so that'll multiply out to 0. So any way you slice it, it's 0 for all time. So if I have 0 for all time and then I integrate it, I'm going to achieve my final answer that tells me that y, for this particular value of t that I've drawn, equals 0. Okay, and for this particular value of t, let's see if we can think about what a value of t would be that would yield this particular picture. So for example, if I picked, I don't know, t equals -1 or t equals -2 or anything like that, this would be my picture. Okay, and in fact, as long as t is negative, then this will be my picture. Okay, then that means my square pulse will be shifted to the left of the y-axis. Alright, so it appears that as long as t is negative, that y of t will equal 0. Well, that's good, but that's not a very interesting result. So let's try another value of t. So I'm going to take my exact same picture now, and I'm just going to use a slightly different value of t. So maybe I should draw these so they line up. Okay. So here's another value of t. So the leading edge of the square pulse is still t. The trailing edge is still t minus 1. And all I've done now is I'm using a different value of t. And in a minute we'll discuss what that different value of t might equal. Let me just draw some dashed lines here so we can line everything up. This is still 1, and that's still 1. Okay. So if I multiply x of tau with h of t minus tau for this particular value of t, now I'm going to get something that isn't 0 for all tau. Now I'm going to get a function that looks like this. It's going to be 1 times 1 minus tau until I get to t, and then after that it'll be 0 again. So we have that. So to be clear, this is 1 times 1 minus tau. This is t, and this is 0. So if I want to figure out what y of t equals for this particular value of t that I've drawn, that'll be the integral from 0 to t of 1 minus tau d tau, and we can just integrate that normally. So if I integrate that normally, I'm going to get tau minus 1/2 tau squared on the limits from 0 to t, and that will equal t minus 1/2 t squared. And there you go. That's my equation for y of t. So now I have to ask myself, for what values of t does this integral apply? And I think we can make a pretty good argument that this particular picture that I've drawn in blue will apply as long as t is between 0 and 1. As long as t is between 0 and 1, I'm going to get the picture and the integral that I've drawn in blue. So let me make a note of that. T has to be, for this case, between 0 and 1. And if you don't understand why it has to be between 0 and 1, probably the best thing to do is to shift it a little more, and then you'll see why it looks different. So let's try taking my square pulse now and shifting it a little bit more. So once again, it's still the same function. The leading edge is still t. The trailing edge is still t minus 1. I'm just using a different value of t. And in this case, when I multiply x of tau and h of t minus tau, now I'm going to get something different. Now I'm going to get 0 for all tau, except over here. Okay. Now, this is still 1 minus tau, but now 1 minus tau occurs over a different range. Now it's going to occur from t minus 1 to 1. Okay, so that's going to be my x of tau times h of t minus tau. And if I want to know what y of t equals, for this case, for this particular value of t, well, now I'm going to integrate 1 minus tau, that's the function, but now it's going to go from t minus 1 until 1, d tau. And once again, let's integrate that. So that'll be tau minus 1/2 tau squared from t minus 1 to 1. And if I do my substitution, that's going to give me 1/2 minus the quantity t minus 1 minus 1/2 t minus 1 squared. And that is going to work out to 1/2 minus t plus 1 plus 1/2 t squared minus t minus 2t minus t minus 1/2. No, plus 1/2, I beg your pardon. Plus 1/2. Does that look right? T squared minus, yes, okay. And putting it all together, that leaves me with 2 minus t, 2 minus 2t minus, plus 1/2 t squared. Okay, I feel pretty good about that. Let's double check my answer. That's 2 minus 2. Okay, I think we got it right. And then, so now we have to ask ourselves again, over what range of values of t will this be the solution? And to work this out, I think we have to realize that as long as t minus 1 is between 0 and 1, we'll have the green picture, or in other words, we'll have the green integral. Okay, so as long as t minus 1 is between 0 and 1, then we'll get the integral that I'm describing here. Well, in order for t minus 1 to be between 0 and 1, that would imply that t has to be bigger than 1 but less than 2. Okay, so this is my answer, but only if t is between 1 and 2. And then finally, we have the last case where we shift it even more. And once again, this is t. This is t minus 1. And in this case, we're back to having nothing to integrate, okay, because there's no overlap between the two functions. So for that last case, y of t will equal 0 again. And that will always be the case when t minus 1, when this trailing edge is greater than 1, or in other words, when t is greater than 2. So t is greater than 2. And now I'm done. I've defined y of t for all time. So if I put it together, I get the following. So here's t, here's y of t, and I'm going to define my x-axis, 0, 1, 2. Okay, that should be good. Now we've said that for negative time, I have y of t is 0. For t greater than 2, I have t is 0. Then I have for t between 0 and 1, I have that quadratic, and that's a downwards pointing quadratic because it has a negative t squared term. And then for t between 1 and 2, I have this equation, and if I plot that, I'm going to get this. And this will be 1/2. Okay, I've basically just plugged the numbers into the two plots, into the two equations, and that's how it's going to look. And that's my y of t. Okay, it's a piecewise solution that we've worked out, but we get the value for all time. So in doing this, the trick is really to think about how many different integrals you need to do. Essentially, you need to do one different integral every time the limits of integration would change or the functions would change or something. And the only way to get good at that is by doing a few examples and then getting the knack of it. But hopefully this will be helpful. So one thing you can do if you want to practice is do the same integral again, but instead of swapping x and h the way I did, do it the original way. Keep x of t the way it is and then flip h of t around instead of flipping x of t around. And if you do that, the math will be a little bit more difficult, but if you apply the integral, you should still get the same exact answer because there's only one solution. So that's something I'm going to encourage everyone to do for practice is to do that convolution integral that way. So the last thing I want to do is I want to show you an animation of this process. So what you're looking at here, at the top you have x of tau, which is exactly the same x of tau we were looking at. And on the middle row, on the second row in yellow, we have h of t minus tau. And here there's no h of t minus tau to see because it's been shifted all the way to the left. Let me drag it a little bit to the right. And then the purple line is x of tau times h of t minus tau, which is 0 for all time. And then finally you have y of t, which is the integral of the purple line. So this is just an animation of what we've been doing before. And I'll draw your attention to the fact that, here, let me drag this over a little more. Let's see, right now, t is equal to -1/2. So therefore, you expect that the yellow signal, which is the flipped version of of my h of t, of my h of tau, it's shifted to the left by 1/2 unit. And because there's no overlap, there's nothing left to talk about. So let's keep shifting it right a little bit more. And already we can see that as soon as t gets to equal 0, there's going to start to be overlap between the red and the yellow signal. So if I up t to 0.1, now you can see that there's overlap between x of tau and h of t minus tau, and their product is shown in the purple function. And then finally, I don't know if you can tell in the video, but underneath the blue function I've shaded in blue, and that's the area that we're integrating. And that's what you see in the green signal. So for example, the area under the curve equals, I don't know, whatever it equals, and that's going to be the value of y of t. And keep in mind that for this particular case, t is equal to 1/10, 0.1, and that's why I've just created the integral that I've created applies to t equals 0.1. Okay, now as I slide it over, the area of overlap is going to increase, and therefore the integral is going to increase in a concave down fashion. And then if I keep sliding, now the area is going to get smaller, which means y of t is going to get smaller. And then finally, when t minus 1 lines up with 1, or in other words, when t equals 2, there's no more overlap between them anymore, and I get 0. So I'll be posting a copy of this code along with this video, and you should definitely download it and play around with it and see if it helps you understand the process. All right.